Hello, this is Rob Crater with RKR Engineering, here to give you an overview of the capabilities of Pressio, which means pressure in Catalan, think Barcelona, but in English it means the simplest, most efficient, and accurate software product for performing overpressure protection, design, analysis, and evaluations, or relief valve studies, as a lot of people like to refer to them as. But before we get right to it, I would like to give you a one-slide introduction to RKR Engineering for those of you that aren't familiar. RKR Engineering was established in 2011 and over the last 13 years has performed hundreds of successful projects in a variety of areas, including small implant design projects, air dispersion analysis using FAST from DNV Technica, development of pipe specifications, process simulation using all the major process simulators, and pipe stress analysis using Caesar 2, primarily in support of our flagship service, which is Overpressure Protection Design, Analysis, and Documentation, which RKR has over 30 years of experience performing these types of evaluations. Pressio is the engine that drives the work RKR performs on relief systems. And while I am the only employee of RKR Engineering, I have a network of consultants, as well as have teamed up with larger engineering companies to greatly increase bandwidth. I've heard a lot that, oh, you're only one person, but that really is not the case. And you can learn more at rkrengineering.com. Now on to Pressio. Pressio is overpressure protection software for the oil and gas industry that has primarily been used in the upstream and midstream space. It's an MS Access relational database system that is linked to thermodynamic engines to ensure accuracy and efficiency. The typical approach used by most engineering companies is to go to the process simulator, simulate whatever you need to simulate to get your fluid properties, and then take the values and then input them into an Excel spreadsheet that's been passed around from company to company, perform the calculations, and do it that way. In this manner, it takes time to pull the numbers from the process simulator and put them in Excel, but more importantly, it introduces an opportunity for error. Pressio solves that problem. It's deployable as a runtime access database solution, which means you don't necessarily have to have access on your computer to run Pressio. And while Pressio is kind of a new name for this, it has been in use in a variety of forms as it's developed over the years to evaluate thousands of relief devices for a variety of companies, and maybe one of those companies is yours. And it's really relief system documentation at your fingertips. It's an information management system for your pressure relief system. And it's really quite simple, as you will see. It's everything you need and nothing you don't. So let's check it out. I'll get my face off your computer screen and we'll take it for a test drive. When Pressio is opened, it will open to the plant search form. The purpose of the plant search form is to find the particular facility that you're interested in. This happens to be RKR's database that contains most of the work that's been done over the years. So there are a lot of different companies in here, as you can see, and we'll just select one, kind of show you how this works. So we'll pick on MPLX. Now it'll filter the database for only facilities owned by MPLX, and you can see all of the different facilities that have been looked at over the years. So we'll just select one, Black's Fork. And then normally we just open the main form and get to work. A few other things to show you here. First, you can preview a device summary. And this is a summary of all the relief devices that are in the database. The tag, drawing, equipment, tag, description, make, model, size, set, even the design case, required relief rate, device capacity, pressure drops. So a real good summary of all the different relief devices in the facility. And you'll see a few things in red. Those would be issues. For example, the inlet pressure drop was too high, therefore this value is red. So you can quickly see if you have any any issues from a device standpoint. Also, you can preview all the recommendations that came out of the evaluation. These are all the issues that were identified, things like inlet pressure drop too high, outlet pressure drop too high, relief device undersized. And so you'll see device tag, drawing, equipment tag, and here's our recommendation. It is recommended to remote sense the pilot for inlet pressure drop, things of that nature. So all of that is in one consolidated report. Easy to keep track of, easy to knock them out like PHA action items. And down here is the select data file. Just a little bit on this. Pressio is a split database. So the front end, which is all the forms, the calculations, the code, etc., is in one database. And then the data, the actual input values, output values, and so forth, is in a separate data file that is linked to the front end. So it's called a split database. The particular database we're looking at here is the General Master Relief Database, as I said, which is the one RKR uses for most of its work. Western Midstream happens to have their own database, I guess because they're special. And so if I wanted to link to that, I would just select that and link the data file. So if you had multiple operating regions or something of that nature and you wanted them in separate databases, you could do that this way. But back to the main purpose here. We're going to open the main form, but we'll open it to RKR demo facility. And here we are. And so we'll open the main form.
In the upper left, you should see some general information, company name, facility, such as gas plant XYZ, something of that nature, and some project information. But the real dashboard and navigation is right here with our equipment summary that lists by tag each piece of equipment that's been entered into the database for this facility. And on the relief device summary side, similarly, by tag each relief device that's been entered for this facility into the database. You can open up a particular piece of equipment and take a look real quick, such as the fuel gas scrubber. Open that up. This is the scenario description we're going to talk about in a second. Here's the PSV that's protecting it, so I could go look at the PSV. Close out, close out. Or I could go on the relief device side and look at the very same PSV and go to the equipment. So either way, you can access the information. As you will see as we continue to go through the various forms, the analysis spends a lot of time from equipment side evaluating scenarios and relief requirements. Therefore, a lot of the access to the information is over here on the equipment side. So with that, let's go ahead and take a look at one, and let's look at the low pressure separator. When any piece of equipment is open, in this case, our low pressure separator, V2010, the scenario form will be displayed. The scenario form has some basic information on your equipment in the upper left, tag number, description from the P&ID drawing number, MAWP, MAWT, MDMT. In addition, there's some information about where we got the basis information for this particular piece of equipment. Did I have a U1A, vendor drawing, nameplate, etc.? In the middle are the related relief devices, and these are the relief devices that are protecting this particular piece of equipment. In this case, we have the typical one PSV, one piece of equipment relationship. So PSV 2010 is protecting V2010. There could be multiple relief devices, or in some cases, no relief devices. And this is particularly useful if you're using an equipment-based approach where each and every piece of equipment is evaluated for potential overpressure scenarios. Underneath, we have recommendations, and these are typically recommendations that are made to address deficiencies that were found during this analysis, and then notes or any notes that might be relevant to the analysis, but not particularly specific recommendations for changes. Under the scenario summary, we'll see each scenario that was considered for this piece of equipment. These scenarios could be the basis case or worst case, design case. Could be credible, not credible, maybe credible, but I didn't calculate it out, and so forth. For each credible or basis case scenario, there's usually a calculation method assigned, and this is the calculation method that's going to be used to quantify the required relief rate. And as you can see, there are numerous different forms for calculating required relief rates. Everything from low pressure tank type venting calculations to our typical external fire on a pressure vessel. The rationale, again, is entered whether this scenario is credible or not, and explains kind of the analysis process for determining, yes, this is a credible overpressure scenario, or no, it's not. So I'd like to spend a lot of time here making very clear how this determination was made. Further over to the right, we have device description and value. These are key instruments, settings, etc., that impact this particular scenario. So in this case, we have a level control valve failure. So I'm listing out the level control valve. I'm telling you it's a 2-inch Fisher D4 with 1-inch M-form trim. And I'm giving you the CV and XT that are needed for the capacity calculations. I'm also telling you what the upstream pressure was. That's the pressure upstream of this particular control valve, and the downstream pressure, which is typically the relief pressure, which in this case is 250 times 1.1 or 275. The required rate and area are brought back in from the calculation form. So as you can see, we simply build up our different scenarios that were considered. In this case, we have 5 scenarios that were considered. If I needed to consider an additional one, I would just add another scenario. I'd say it's not credible. And there we go. We have another scenario. So that's the overpressure scenario form in a nutshell. Next thing we will do is dive into a required relief rate calculation. And to do that, we'll just start with our LV 8500B failure open scenario that we're just discussing. So if we select that and click Open Calc, we will see the vapor control valve failure form. The vapor control valve failure form opens and reminds us that we are working on V2010, the low pressure separator, LV 8500B failure open scenario. All of the required relief rate calculation forms are organized in a similar manner. At the top, you'll have equipment data, and this data was pulled in directly from the overpressure scenario form that we just left. Then below that, on the left, we'll have the scenario input data. That is all the data that's required, and it's shown in blue, to be entered such that I can evaluate this scenario, the relief device, and the inlet and outlet pressure drops. On the right is the scenario output data, which is the output data that is calculated for this particular scenario and includes values that are relevant for this particular type of scenario. So for example, for a vapor control valve failure, you're going to have an FK value, a Y value, an FP value, things that would not be present for an external fire scenario. So those sorts of calculated results are put in the scenario output data. So this section will be reasonably customized for each type of scenario calculation or required relief rate calculation. Down below, we have the scenario calculation results. This section will look very similar for each of the required relief rate calculations. This is all the fluid properties and details at the relief conditions, as well as at the outlet conditions. That's the constant back pressure that were used to evaluate the capacity of the relief device, as well as the inlet and outlet pressure drops. And these capacities and pressure drops are calculated in the relief device sizing form that we'll see in a minute. So there are more detailed videos available for each calculation, our required relief rate calculation form. So I'm going to go into the details of each input. But a few things in general, the upper right of each form is a help button, which will take you to the help file, which is on rkrengineering.com. Directly to that, I will move that over so you can see that. Here it's showing you the database version of this particular form with all the inputs and outputs. Gives you a description of each and every input, the calculation methods, including detailed equations that are used. In this case, the control valve failure scenario form will handle Kimray valves, the traditional Fisher method with CG and C1, as well as the universal or most popular method, our IEC method, which uses CVs and XTs. But all the basis, all the calculations, all the details are provided in the help documentation that can be accessed by clicking the help button. Other things of interest, if you hover over a particular form or field, you will see a quick description. What am I supposed to put in this particular field? Like for additional flow, well, I can add, that's any flow to be added, perhaps through a bypass or subtracted, perhaps for outflow from the downstream equipment to from the control valve flow. So anytime you're a little stuck on a particular input, the quick way is to hover over it and get a quick description of what is there. The last thing, kind of in general on all of these required relief rate calculation forms, is the thermodynamics. Thermodynamics is available from NIST, the National Institute of Science and Technology, that's Ref Prop 10, but also from Schlumberger's Symmetry program, which some people will know as VMG. This calculation form is integrated with those thermodynamics, allowing access to all these different property packages that are a part of Symmetry. So you can pretty much find a thermal package for anything, any compound that you're looking for. In this case, we just have natural gas. So if we open that particular stream, we can see the composition of that gas. We can normalize that composition. This has to equal 1, similar to a process simulator. We can add new components, and you can see all the different components that are listed here are available for use. And that's how the stream is defined. And one of the key aspects of Pressio is this integration of thermodynamics, such that you don't have to go back and forth from a process simulator to a spreadsheet and so forth, typing in the same number in multiple locations, creating difficulties with consistency and that sort of thing. That's the basics of most of the required relief rate calculation forms. Now and as I said, there are more detailed videos on each one of these forms, so they go into the discussion of the actual inputs, a little bit more about the equations used, and a little bit more about the results. But with that, let's go back scenario screen and take a look at things from the PSV side. So our PSV is PSV 2010. Again, protecting our low pressure separator. As we showed earlier, just hit open RD. And the PSV form will show up. And this PSV form has a lot of the information that you would normally see on an ISA data sheet, so it should look familiar. But in the upper left, tag number, drawing, basic information about the PSV, what it's protecting, a little bit about its operating fluid and the relief fluid. This is important since sometimes it's operating in liquid, but the relief stream is vapor and so forth. So this gives you a specific relief fluid and relief phase. Over on the right, we have our related equipment. We showed that earlier from the PSV. You can go back to the equipment, which will take us back to our scenario sheet. And again, there could be one piece of equipment or multiple pieces of equipment here. We'll get back to these buttons here with the piping and the sizing. Underneath that, similar to the equipment, we have some information about the PSV basis and the piping basis. This is just telling us where I found the detailed information on the relief valve. Did I have a test report? Did I look at the nameplate in the field, vendor specs, a photo, etc.? piping basis, similarly, was it from a 3D model, maybe a GA or an ISO, from the field, a photo, and so forth. Underneath all that is the basic information, mechanical information on the relief valve. So manufacturer, model number, serial number. In this case, I'm speccing a new relief device. So I've just put new purchase pending selection of the actual manufacturer and model number. And because that has not been selected yet, I'm going to use the API default values for orifices, the area, and the KDs. So in this case, I have an N orifice. Here's the API area for that orifice, inlet and outlet connections, flange types or threaded, type of relief valve, very important, pilot operated, conventional, and so forth. Operating conditions, set pressure, cold set. Here's our KD liquid and KD vapor. So these again are the API default values that I'm sure you'll recognize. And then the sizing basis, kind of once this is all concluded, we'll determine what the sizing basis or worst case is for this relief valve. But at this point, we know it's LV8500B failure open. A little bit of information on the materials for this particular relief device. In this case, nothing special. Some notes. In this case, we've got a modulating pilot, so I just put a note in here that the pressure drops were based on the required relief rate as opposed to the actual capacity, which is the typical way to handle a modulating pilot relief valve per API. And then finally down here under revisions, as I have revision control, so here I'm just issuing it for quote. Perhaps when we select the actual valve and install it, we'll go to Rev 0 and have an IFC issue with the manufacturer, model number, and serial number available, as well as the actual KD values and orifice area. And along those lines, there are some of the more common relief valves in this database where I can get the MBIC values or Red Book values. So let's say I have a Mercer 9500 pilot operated relief valve. If I type that in, I say get MB values. You'll see the orifice area is now 4.909, and you can look that up in the Red Book. That's what it'll say. And you'll see that the KD vapor is 0.87. The KD liquid has stayed at 0.65 because this particular model number is only certified for vapor. But just a little something to save some time and increase accuracy for specific manufacturers' relief valves. But I'm going to go back to my API values for the rest of this sizing. There we are, we're back. Now, if we go up here, if we go to sizing, we'll see up at the top, here's our PSV and so forth. Here are the related scenarios. Now, if you'll recall, there were 5 scenarios for this particular relief device. Of those 5, 3 were quantified, and here they are. We have our restriction orifice calculation, our control valve failure that we went through in a little bit more detail, and then a fire case. So these 3 scenarios need to be sized both for the relief valve capacity as well as inlet and outlet pressure drops, and that's what we're going to do now. On the left side, we'll have a bunch of information that was brought in from the previous PSV form. So some mechanical characteristic of the relief valve. Here's our API orifice area, for example, set pressure, allowable overpressure. Again, all brought in from the PSV form. Now, when you first open this, there'll be a lot of blanks over on the right side. And as I told you, when we did the required relief rate calculations, we determined all the fluid properties that were going to be required to evaluate the capacity of the relief valve, as well as analyze the inlet and outlet pressure drops. And we do have that information available, and all we have to do is select the particular scenario that we want to evaluate. In this case, we'll go ahead and do our vapor control valve failure case and hit get scenario data, which populates all the various fluid properties, the required relief rate, the thermo package I'm going to use, how I'm going to do the outlet pipe pressure drops. In this case, I'm going to use an adiabatic correlation. Again, More details on all these calculations are available at rkrengineering.com. But with that, I should have all the information here that I need to calculate. So the first thing I'm going to do is calculate the actual relief device capacity by hitting the calculate button. And you can see there it is. It fills in the actual capacity, the required area, and so forth. It also tells you when the relief valve is the flow is gonna choke across the relief valve. And so that is the capacity information for the relief device. Next, we're gonna calculate the inlet and outlet pressure drops. This is accomplished by simply entering the pipe, valve, and fittings from the vessel to the inlet of the relief valve. This is accomplished by selecting the MPS. You can see here there's all the typical MPS sizes for pipe, schedule such that it knows the inner diameter, the fitting type, here are the types of fittings that are available, the quantity or number of fittings, or in the case of pipe, the length in feet, and then for contractions and expansions, a beta ratio. With all that information entered, it's as simple as hitting calculate inlet. And here's your inlet pressure drop, 1.1 psi, 0.5% of set. So we're in good shape there. The same thing applies to the outlet, and the pipe, valve, and fittings are entered in the same manner. And once done, you simply hit calculate outlet. And the outlet pressure drop will be calculated, including the exit pressure. This will be the choke pressure at the last fitting. So at the exit to atmosphere in this case, the 6-inch pipe, the flow is choked and the choke pressure is 5.4 psig. The total built up back pressure is 14.5, yielding 5.8% of set pressure for the back pressure. And of course, that is acceptable for even a conventional valve, although this is a pilot operated relief valve. So with that, the last thing to do is reevaluate the capacity such that we can evaluate the reaction force, which of course depends on this exit pressure that we just calculated. So if we simply hit calculate, here's our reaction force. In order to update back to the scenario required relief rate calculation such that we can see these inlet pressure drops, we just simply hit update scenario. So at that point, this vapor control valve failure case, our design case, has been fully evaluated, both in terms of capacity as well as determining the inlet and outlet pressure drops and whether they are acceptable based on this particular relief device, and they are. That process is completed for the other two scenarios in the same manner, and at that point, we are finished. So we have evaluated these three scenarios, size of relief valve, checked all the inlet and outlet pressure drops, and this one is complete. So if we exit back to our scenario form, here we go. And we can pull up, preview our scenario sheet, and you can see all the different scenarios, everything we talked about. Here's our required rates, pressure drops, and so forth. So at this point, it's just a matter of figuring out how you want to print out and store all this information. And of course, you can always just store it right here in the database. Thank you for taking the nickel tour. Hope you enjoyed it. And again, more detailed information, because with relief valves, the devil is always in the details, is located on rkrengineering.com. Thank you.